studied the ordinary rectifiers where a diode is used. The rectifiers can be considered as an uncontrolled rectifier because the output voltage cannot be controlled in case of diode rectifiers, whereas that can be controlled in case of phase controlled rectifiers, which we are going to study. So this is the major difference between the uncontrolled rectifiers and the controlled rectifiers. So let us focus on the other differences. As I said, in case of uncontrolled rectifiers, we cannot control the output waveform. Means nothing but it is possible for us to get only fixed DC voltage in case of uncontrolled rectifier. If you are talking about a conduction angle of a diode, means when P type of material is forward biased with respect to N type, means nothing but P is connected to positive and N is connected to negative. That time when voltage is above the knee voltage, 0.7 for germanium and 0.3 for silicon, if it crosses that voltage, then the device will turn on and the diode will act as a closed switch and will allow the current to flow from anode to cathode. That is what we had studied and we know it. So the conduction angle in case of uncontrolled rectifier is 180 degree. So each diode conducts for 180 degree. In case of half wave rectifier, we are using only one diode, so we will be getting output voltage only for 180 degree, whereas for 180 degree to 360 degree, that is from pi to 2 pi, the output voltage will be 0. That is again you had studied. The next is, we cannot control the output voltage in case of uncontrolled rectifiers. The fixed DC voltage is only available, and in case of single wave, in case of half wave rectifier, in case of single phase half wave rectifier, the output voltage VDC can be given by Vm upon pi, which is constant for a given input voltage. In case of full wave rectifier, it is twice Vm by pi, that is also constant, where in case of full wave rectifier, for half, one diode will be conducting and for another cycle, the next diode will be conducting. Means again, the conduction angle of each diode is limited to 180 degree, and this is what in case of uncontrolled rectifier. Whereas totally opposite of it, in case of controlled rectifier, I can control the angle alpha. Means nothing but the firing angle of thyristor can be controlled. As you see in case of structure of silicon controlled rectifier, it is a PNPN structure. Even though forward bias is applied across it, device is not going to turn on, it will be in forward blocking state. So junction J1, as I told you, junction J1 will be in forward bias, junction J3 will be in forward bias, but because of junction J2, current will not flow from anode to cathode and device will be in forward blocking state. When we apply and get signal, then and then only the device is going to turn on, and when to apply the get signal, that can be user defined, that can be user controlled. So I can control the firing angle alpha in case of silicon controlled rectifier. We can control the conduction angle of a output voltage, and conduction angle of an output voltage can be from 0 degree to 180 degree. So that is what possible, and in this way we can control the output voltage in case of controlled rectifier. Okay friends, so as I tell you at the start only, there are plenty of applications of this AC to DC converters. So the converters can be used, this AC to DC converters can be used in almost all the applications where the DC motors are used. Maybe example, steel mills, maybe example, paper and textile mills, and so on. We can use this AC to DC converters in all the applications. Say for example, where DC traction is used, which is played from AC traction. So in all these cases, we may need an AC to DC converters. Then electrochemical and electrometallurgical processes need AC to DC conversion. Then magnetic power supplies need AC to DC conversion. And portable and hand tools need AC to DC conversion. And as I told, there are many household applications where you've seen the application of AC to DC converter, that is nothing but uncontrolled rectifiers. Maybe example, your battery mobile charger is one of the example, maybe your television set, maybe your radio, and so on. Many applications you might be finding where they're converting AC to DC. Now let us focus on classification of these rectifiers or converters. Now onwards, I'll be using word converters. Means whenever we are using an SCRs, the rectifiers are called as in converters, and in case of uncontrolled rectifiers, these are designated as, or these are said as only rectifiers. So these converters, that is AC to DC conversion circuitries can be mainly classified into two types, that is single phase and three phase. Where the power requirement is low and medium, we can go for single phase converters, whereas in case of industry applications where we want to drive heavy DC drives, heavy DC motors, it is essential to go for three phase. So basically these are classified as single phase converters and three phase converters. Then in case of single phase converters, this can be again classified into different categories depending upon the circuit configuration used. It may be classified first on broad basis as half wave and full wave, means nothing but single phase half wave converters and single phase full wave converters. If conduction is only for 0 to 180 degree, then it is called as a half wave, whereas if conduction is there for both the cycles, that is positive cycle and negative cycle, it is called as full wave rectifier or full wave converter. Now the full wave converter can be again classified into two different basic categories depending upon the configuration used. Either it is called as a center tap single phase full wave control converter using center tap transformer or using bridge connection. So this can be classified as either it is M2 connection or B2 connection. Both are having its own advantages and its limitations. The next type will be this bridge configuration, can be again classified depending upon the configuration used. This can be again classified into semi-converter and full converter. So if we are using all the four elements as an SCRs in case of bridge configuration, it is called as full converter, whereas we can go for two diodes and two SCRs, which is called as a semi-converter. In semi-converter again, depending on the connection of the SCRs, either in one branch or in two different branches, this can be further classified as symmetrical configuration and asymmetrical configuration. So overall we can conclude that the classification can be done first on the basis of input supply, that is single phase and three phase. Then again single phase can be classified into two broad categories, half wave and full wave. Full wave can be categorized as center tap transformer using center tap transformer, and second is the bridge configuration. Bridge configuration can be classified as symmetrical and asymmetrical configuration. So same classification is there in case of three phase also. In case of three phase you will find half wave and full wave. In case of full wave you will find semi converter bridge and full converter bridge. So this is what the classification of the AC to DC converters. Now let us